The last speaker for this session will be Alex Volfovsky from Duke University. Let's welcome Alex.
All righty. Great. Well, thank you to the organizers, to Wells Fargo and Temple for having us. I'm really excited to do things in person again, so we should keep the momentum going on that. I'm going to tell you a little bit about some work that we've been doing on different methods for observational studies. And we're going to leverage a little bit of what Ed has done, but we're going to concentrate on settings where you have high-stakes decisions and you really care about why the effect that you're estimating is whatever it is that you're estimating. This is work with the Almost Matching Exactly lab at Duke. It's run by myself, Cynthia Rudin, and Sudeepa Roy, and we have a ton of great students who have been doing a lot of really great stuff. So the work that I'll talk about today actually covers sort of pretty much everybody's work. So yeah. All right. So I'm going to think about causal inference in sort of this Niemannian framework that was formalized by Don Rubin into the potential outcomes framework. So you would imagine that you have n individuals, and they can be assigned to potential treatments T1, T2, T3 through Tn. And for simplicity, let's just have binary treatments here. And a key sort of insight was that each individual could live in lots of different universes where different types of treatments were assigned. And so these are potential outcomes, yi, and inconveniently, they need to be indexed by the whole treatment vector. And while I'm not going to talk about what to do with that when you can't make simplifying assumptions, that is actually a universe that I think a lot of financial data lives in, where lots of different things are happening, lots of different shocks, and those shocks are working in concert. And you really can't just think about the shock that I experience. You also have to think about the shock that somebody else experienced and how that affects my outcomes. But for our purposes, we'll make the standard simplifying assumption that my treatment affects me and nobody else. So I'm going to abuse notation now, and we're going to forget about indexing the yi's by all the T1 through Tn, and now just we have a yi of 0. What is it that my universe looks like? What is that my outcome looks like if I were not treated? And yi of 1 is what is my potential outcome if I were treated? Once we've sort of decided that this is the universe we live in, we can ask questions. Well, what is the treatment effect that is received on average due to this treatment in a particular population? So you can think about you have a population of n people. What is yi1 minus yi0 for all of these people on average? And your spidey senses should be tingling because you only get to observe one universe, right? We continue, even though we clearly live in a simulation, we only get to observe one version of it. And now that you only have yi1 or yi0 for each individual, it's not obvious how to estimate this object. But thanks to a lot of work by a lot of people, it turns out that under standard assumptions, you can, for example, estimate this average treatment effect with this naive difference in means. So that's great. This estimator has really nice statistical properties under some assumptions. And so you'd think that this is where the story ends. But in reality, there are two other things that are happening. Either you are in a randomized universe where there's some experimenter that flips a coin or makes decisions about who is going to get what kind of treatment. Or, more likely, you're in an observational universe where people get to select into treatment. And that's going to be a problem for us, potentially. So the general goal of causal inference is to estimate or understand contrasts between counterfactuals or between potential outcomes. So they don't have to be differences in means. They could be odds ratios or any other function. We're going to think about some other functions as well. And randomized experiments are gold standards because they sort of allow you to move away from all of these other problems that exist in the universe because people exist in the universe. And I will borrow a phrase from Don, that randomization has a prophylactic effect guarding against Lots and lots of different problems that exist in the world. And so if you're in a randomized universe, you can just use that naive Neymanian estimator and do really, really well at estimating the average treatment effect. Oops. But what if you can't randomize? And so once you can't randomize, people have behaviors, and some people might choose to take treatment more often than others. And suddenly, if you don't take that selection process into account, you might end up comparing people who are not necessarily comparable, or comparing firms that are not necessarily comparable. My claim is that the counterpart to randomization is actually exact matching. If by some process you've collected all of the information that you could have possibly collected about everybody in your study, and that information can be matched on exactly. You can find twins. One of those twins chose to take treatment. One of the twins chose to take control. I would say that's as good as doing randomization. But, there's a really nice example where even if you only have 5 covariates, there's so many different combinations that this just doesn't work. And so you most likely will not be able to do that. And so the question that comes up to us is, how do you do almost exact matching? And you can sort of translate that into a statistical or an engineering problem of what is the distance metric that matters on which you want to do matching. And so for us, it's going to be a distance metric learning problem of actually solving this for observational studies. This is a very incomplete list of prior literature on matching. I want to highlight Rosenbaum and Rubin, 1983. This is a propensity score paper, probably the most used mechanism for observational causal inference, where you estimate the probability of somebody taking treatment given their covariates. And then you can, well, in my case, match on the propensity score, and you can find people who, even though one of them took treatment, one of them took control, they have the same probability of taking treatment. And again, under some conditions, for some quantities of interest, some estimands, this is actually as good as it gets. You can get really high quality estimates. However, I will argue that not only do you want to get high quality estimates, but you also want to be able to interpret or explain why you made that estimate. And while you might get something that has really nice statistical properties, it could still lead you to having something that is not explainable to the layperson. So this is a quote from that paper where I just highlighted a few things that I think are informative of what it is that we're interested in doing. So subclassification is really exact matching. And if you can do subclassification, you can then do exact comparisons between individuals who look identical in all the relevant things. And once you can do that, you can be persuasive because you have this intuitive comparison. It is reproducible. It's easy to explain. And nobody is going to tell you that you did something. It's very clear what you have done. And it would be great if Don stopped writing here, but he wrote the next sentence that says, actually, well, that's great, but you can't really do that because if you have even just a few potential covariates of interest, then the number of subclasses or the number of exact comparisons that you'd need grows really, really, really fast. And so you're going to end up not being able to make causal statements for most of the people in your setting. And so you can't really do exact matching, but this is really the motivation. Our goal is to sort of get over that hump at the end of not being able to do exact matches, and you want to do nearly exact matches. And this is why. So this is a data set. We're looking at the Lalonde data. So this is a data set on a job training program that was studied. And it's a really nice data set because there's an experimental data, which involves both people who were treated and who were not treated. And we know that somebody randomized them into those categories. And so we can actually estimate really with pretty good precision what is the treatment effect of that program. As a counterpart, there's lots and lots of observational data on people who did not participate in this program, but for whom we have both outcome information and some really meaningful covariates that we think might have helped them select, would have helped them select into the program potentially. So here what I'm showing you is a matched group using prognostic score matching. Prognostic score is the counterpart to propensity score matching, where instead of matching on probability of treatment, you match on some estimate of baseline outcome, so on y0. And I picked a query unit, so that's the top line. And what I'm highlighting here is weird things. This isn't to say that you can't do high-quality estimation using prognostic score matching, but why would you trust the estimate, or how would you explain the estimate that you've constructed for each individual or for the overall if you have such discrepancies in the matched groups? Right? So for some reason, it looks like the income in 1975 is not matched really well. Right? On the other hand, one of the methods that I'll show you, our approach, same query unit. This is the match group for us. And look, we've matched exactly on the income in 1975 because we've identified that that's an important thing to match on. We've identified that matching on age is really important, so we made more of an effort to match on age, and so on. Now, there's a little bit of information that you need to know. We are doing matching on the whole covariate space, whereas prognostic score matching and propensity score matching have actually projected down to a single dimension, which makes the problem substantially more difficult to construct sort of high-quality match groups like this. But nonetheless, sort of our goal is to be able to construct match groups like that I can give to somebody who is a subject matter expert, and they can tell me, yeah, this looks like I would believe whatever estimates you get out of these match groups. All right. So I will suggest that a reasonable causal inference pipeline is, for our purposes, construct match groups, have subject matter experts evaluate them. Are they good? And this translates in, for medical data, which we've been working a lot with some physicians, into a chart review. What they do is they read the charts of the people that we've matched based on some machine learning approach, and they decide whether or not the people look comparable on things that we might not have measured, actually, right? And then you might want to update the match groups, and then you want to do the actual causal inference. There's a little bit of very recent work on that step too, and we are sort of thinking about also automating that as well. All right. So we've constructed a bunch of different algorithms that are meant to deal with slightly different setups for the observational problem. I'll talk a little bit about all of them, but DAME, because DAME is just a little bit involved, but it solves the same problem as FLAME. All right, so this is our setup. So we have some covariates X. Y is going to be some observed response. T is a treatment indicator. And we're going to make the assumption that the Y we observe is, in fact, one of your two potential outcomes. We observe either your treated potential outcome or your control potential outcomes. And the quantities of interest could be something like the average treatment effect. But in reality, in high-stakes decision-making, you are worried that there might be heterogeneity among, let's say, patients, or there might be heterogeneity among the units that you're interested in. And so you might actually be interested in something like a conditional average treatment effect. This is frequently written down as an individualized treatment effect, and it's individualized in the sense that it is true that an individual who has those specific covariate values will have this estimate. But this is really just a conditional expectation or conditional averaging. So our goal is to construct match groups that will help us estimate these two quantities, and that they will have sort of high confidence in that. So what does this mean, really? Well, if we knew how to match, if we knew what are important covariates to match on, we would just go ahead and do that. And what that translates to in the discrete case where all of your covariates are discrete, let's say they're all binary because life is easy, is if you know the importance of those covariates, you could try to solve this problem. So for each treated unit, let's imagine our treated units are scarce, and so that's the ones we really want to construct high-quality match groups for. For each treated unit, we would like to find control units that match on as many really important covariates. Right? So this is the notion of almost that we're working towards. So we want to maximize, for example, this theta transpose W, where theta is a selector function, right? It's just a binary indicator of whether or not you match on a covariate 1, 2, 3, etc. Now, you could sort of think about this is sort of a way to get away from the curse of dimensionality. Because, for example, if you didn't have those weights W, and you have thousands upon thousands upon thousands of covariates, but only 5 of them are important, and you try to do almost exact matching like this, you would end up with matching on mainly unimportant covariates. And so here, by incorporating these weights, which some oracle gave you, you're able to actually solve the problem correctly. And what you're going to end up with is match groups for each unit that have a treated person and a bunch of control people, for example, that maximize that equation. But nobody told us what W is, right? There is no oracle. And so we need to do something about that. So let's split our data. So everything I talk about, we're trying to do it by splitting the data into a training set where we get to do whatever machine learning we want on that training set, and a matching set. That matching set is only touched once, and that's the only one where we're going to report estimates from. So I'm going to take my p discrete covariates in my matching set, and I'm going to try to do exact matching there. Let's imagine that I have been able to match a couple of people exactly. That's great. That's as good as it's going to be. It doesn't matter if any of these things are irrelevant to the causal question at hand. You're not introducing any additional bias right now under sort of sufficient regularity assumptions. The next step is to try to figure out what covariates are less important. So pick your favorite model and model y, maybe y given t, in your training data set. And do the most naive variable selection that you can. So let's just find the biggest p-value and say that that's what I'm going to throw away. Then, on those p-1 covariates that are still important, you do exact matching in the matching set. And then you rinse and repeat. So this is a greedy solution to the previous problem. This is flame. This is fast, large scale, almost matching exactly. Dame, which I won't actually discuss, solves the problem exactly. It's not greedy like this, and it's very computationally intensive. So there's some trade-offs on that. What's great with this approach is that it produces a match group for each unit, a measure of quality for that match group. So imagine that nobody matches on anything at all, right? And so you keep throwing away stuff. That measure of match quality could, for example, be minus predictive error, right? So if you can't predict y in your training data, you don't really want to trust those match groups. So, and then for each match group, you can also compute a conditional average treatment effect inside that match group, right? Nothing is stopping you from doing that. You can also take a new unit that comes in and try to figure out which match group to throw it into. And then you have an estimate for that person as well. What's important is that everything in step 2 is completely up to you. You can be as flexible as you want. You can, for example, do BART. which you probably should. So let me just show you one bake-off. So take 30 covariates. They're all binary. And this is the outcome model that generates the data. So only the first 10 covariates have non-zero effect on the y. The other 20 are just sort of noise. And we've induced some kind of confounding. So the x's are different among treated and among controls. There's some correlation between x and t. And what I want, this is a little bit of an unfair comparison between our two methods and propensity score matching, Mahalanobis matching, and GenMatch. It's unfair because those methods are not designed to estimate conditional average treatment effects. And in fact, if you squint and sort of squeeze those numbers down, they do a really good job at estimating the average treatment effect because they're designed for that. But our goal is to get to something like figure A. So figure A is running that previous procedure and stopping when the match quality gets too low. And it turns out that for those people, we get a pretty good estimate. I also want to draw your attention to E, which is causal forests, and that seems to perform really poorly in this setting. And that's because while it's a very flexible method, it's based on random forests, and we have lots of irrelevant covariates, and we know that random forests suffer under that setting. So let's replace that with BART, and you can see BART does really, really well. But what you don't get in the BART figure, even though you get really good estimation of the treatment effects, excuse me, what you don't get is you don't get the interpretability of the match groups. You don't get to talk about, for this value of x, why did I estimate the treatment effect to be this? Excuse me. Okay, so let's look at the general case. If you have discrete and continuous covariates, clearly exact matching becomes meaningless, right? Because what does it mean to match exactly on things that live in RP? But you can still think about, well, let's imagine that some oracle tells you these important W's. And you can translate this problem maybe into this setup where, well, I care about, excuse me, the distance between my treated unit and my control units on the covariates to be small in some metric. And those W's say that I care about being, if W is really, really big, I really care about, I pay a big penalty for mismatching on that unit, and I pay a small penalty for mismatching on another unit. So let's solve that. This is matching after learning to stretch. And what we have here is we're thinking about, well, we have these covariates X, and we need to stretch them out because if we want to start paying a larger penalty, let's imagine they all live in the Euclidean space, we want to start paying a larger Euclidean penalty if we end up mismatching on an important covariate. So defining importance in this way, where what you see sort of as the objective function down there is the, is that a water?
We're full service bank.
Yeah, perfect. Thank you. So if you look at the objective function, all it's asking is that I want to construct matches, I want to estimate a distance metric that allows me to correctly recover the treatment value for each individual based on local treatment people, right? People who are close to them. So turns out it's fairly easy to solve this distance metric learning problem. It's also possible to replace this objective function with something that incorporates information about the amount of unobserved confounding you're worried about or something like that. But we've concentrated on that. And I come back to the Lalonde data, and this is estimating the average treatment effect of being in the program. And the truth here is based on the experiment, so it's experimental truth. And then what we do is we try to estimate that number, 886, using the experimental people, the people who were treated in the NSW, and a bunch of control people from, in this case, the PSID2. And as you can see, there's lots of methods that do more or less well. What's important is that third line, malts pruned, seems to do really, really, really well. We only use about 5 to 10% of the data for training, and we're able to get very low bias at estimating this quantity. The pruning here happens sort of using rules of thumb. It's not by knowing that we want to prune to get to this outcome. Okay. But what if that was not sort of to your liking? What if you actually really believe that there's a good model for the outcome? And you want to do model-based inference, but then your doctor collaborator comes back to you, or your banker comes back to you, and they say, hey, I need to know why we're making this estimate. So let's say that you do BART. Well, can you somehow take the high-quality BART estimate and construct some kind of matching procedure that approximates it? So let's estimate f hat 0 and f hat 1. Those are going to be my sort of very flexible estimates of the potential outcomes under, or the mean of the potential outcomes under treatment and under control. And then I'm going to try to find subsets of the covariate space where those things don't vary too much. And when they don't vary too much, it's fair probably to say that the people in those subsets of the covariate space are similar. And then again, I'm going to go back to a matching set, and I'm going to do matching-based estimation. To sort of make this very concrete, this visual example, I think, is important. What you see on the left-hand side is very similar to what happens, for example, in coarsened exact matching, where before you've done any work, you've decided that I'm going to coarsen my covariate space, let's say, with equal distances. But it's fairly clear, if you're looking at that curve, that it's much more important to match people together who are sort of, to not match people together who are very close in x when x is small versus when x is big. So you need to carefully choose how to do this. And then you have a 2D example of the same thing. What's nice is that this translates into either an integer program, or you can solve this greedily, and the greedy estimation seems to perform pretty well, actually. Again, you don't have to use BART, but you probably should. And again, coming back to the Lalonde data, now looking at the average treatment effect on the treated, our approach using the CPS, and which is another control data set, or the PSID. So the true number is 1794, and our estimates are sort of as close to that as one could hope for. And so just again to remind you, we used a very flexible model, but then those estimates are not model estimates. They're estimates based on the matches we constructed because of that model. The last thing is communication is really important, so having nice visualizations of what's going on is good. And so here's a visualization of those hyperboxes. And you see that, and then we plot this f hat 0. And you see that the hyperboxes get much larger for spaces where f hat 0 is flatter. We have a bunch of theoretical guarantees that these things work. We have guarantees that flame will work and that its bias can be fully characterized. Maltz can be sort of has really nice guarantees from the distance metric learning perspective. And some of the work that I'm really excited about is we have been able to get asymptotic variance estimates based on the matches. And what's really neat here is that we get these asymptotic normality results, and what they mainly rely on is on the fact that that super flexible, high-quality machine learning that we use in our training set is actually high-quality machine learning. And then you get really nice sort of things that you can actually say things about the inference that you're doing based on the matching itself. It's a bunch of papers that have been published on this. we have a demo of this at NeurIPS 2021, which hopefully will go live soon, where you'll be able, maybe now or maybe later, to upload a data set and play around with all of these tools. Otherwise, we have lots of code and tutorials over there. So thank you.